purpose of this video is to look at defining the definite integral as area under a curve. We've already looked at this a little bit, but in the past we have done approximations of the definite integral with using area under a curve. And the way that we did that is, first of all, we did it by counting blocks. And then secondly, we put in rectangles and we looked at Riemann sums. And you'll recall that there are three different kinds of Riemann sums. There's a left endpoint approximation, a right endpoint approximation, and a midpoint approximation. And then finally, we looked at the trapezoidal rule, where it's the same concept. We're collecting area under a curve, but instead of putting rectangles into the region, we put trapezoids and we collect the area. But all of those methods were approximations. So the big question is, how do you find the exact area that is enclosed by a curve, the x-axis, and two endpoints? So let's take a look at this example. We have the function negative x squared plus 5, which is a parabola. And the graph is already provided for you if you have this packet. If not, you can simply copy this down. And the first thing we're going to do is we're going to sketch the rectangles that can be used to approximate the area under the curve from 0 to 2 using 6 partitions. Well, if the interval is from 0 to 2, we're going to subtract the interval 2 minus 0, and we're going to divide that into 6 partitions, so that will give me a common width of 1/3. And so that's the width of all of my rectangles. So if we create the first right endpoint, we'll go to 1/3, and we'll put a dot, 2/3, and a dot, and we're just doing some approximations here. So the first way that we're going to do this is using approximations, right endpoint approximations. So when I draw the rectangle, they're right endpoint approximations, so I'm going to draw from right to left, 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 right to left. I think you can clearly and quickly see that this approximation is going to be an under approximation, because what I'm coloring in red is the amount of area that we're not going to collect by using a right endpoint approximation. The curve is concave down, so this approximation will be too small. It will not be enough area, but it will be an approximation. All right, so now let's go back and let's actually calculate that area. First of all, if we write a definite integral that represents the area, since all of this area is positive, we'll get a positive outcome. We're going to start collecting area at 0. We're going to stop collecting the area at 2. We're going to collect area under f of x dx. So that is the definite integral that represents, and that definite integral represents the exact area under the curve. Number 3 says, set up but do not solve a right endpoint Riemann sum that could be used to approximate the area. Well, we already have our definite integral, so I'll write it again. We're going to collect area from 0 to 2 of f of x dx, and that's going to be approximately. Since we have 6 rectangles with a common width of 1/3, there's my common width. I'll leave that on the outside. The height of the first rectangle would be f of 1/3. The height of the second rectangle would be f of 2/3. The height of the third rectangle would be f of 3/3, which of course is 1. Then we have f of 4/3 plus f of 5/3 plus f of 6/3, which is 2. And I went ahead and calculated that for you. That comes out to be approximately 6.630. So that's an approximation of the area that is bound by the curve, the x-axis, and the endpoints 0 and 2. However, I'd like to find the exact area under the curve. So we've already looked at how our calculator can do integration for us. So I'm going to bring the calculator up. In my y number 1, I already have the function negative x squared plus 5. So if you don't remember how to do this on the calculator, I'm just going to review this with you. I'm going to let the calculator find the exact area for me. I'm going to show you 2 ways to do this. First of all, I'm going to go to the home screen, and I'm going to type math, and I'm going to select number 9. You can either scroll down and choose the 9, or you can type in the 9. And it tells me that I'm going to integrate a function. So the first thing I have to do is tell the calculator what the function is. I have two choices. I can either type the function, literally type the function in, or since I already have the function in y number 1, I can go to vars, and then to y vars, select function, select y number 1. Then a comma. Then we are in terms of x with another comma. The lower bound is 0 with a comma, and the upper bound is 2. Close the parenthesis, press enter, and we can see that the exact area under the curve is 7 1/3. We don't have any units here, so we're just going to go with the numbers 7 1/3. So clearly there is some discrepancy. We said already, why is the discrepancy? Well, the curve is concave down. Therefore, the right endpoint approximation is too small. And that's exactly what happened. We approximated 6.63. However, the exact area is 7 1/3, so we didn't collect all the area. Now, something else I want to show you on the calculator, the other way to find the definite integral is if I go to the graph, and let's just do a zoom 6. There's my graph. I'm going to change the window to go from -1 to 3. That's probably good. Let's see what my graph looks like. Okay, that's fine. I want to collect the area from 0 to 2. So if I do that, another way to do that on my calculator is to go to second trace or second calc. And you can see number 7 is an integral. And it's going to integrate this function. It's asking me for the lower limit, which is 0. The upper limit, which is 2. And it shades the area. Now notice in that shading that we didn't lose any of the area. So this is the exact area that's bound by that curve, 7 1/3. All right, so here's the question. How do we find that area? How do we use rectangles to find the exact area instead of the approximate area? Well, you probably figured out that in this particular example, I used 6 rectangles. Now think about it. If I were to increase the number of rectangles, let's say to 10 rectangles, this red region, this area that we lost, would then decrease because 10 rectangles is going to more closely assume the curve and lose less area. And if 10 rectangles loses less area, then 100 rectangles would lose even less area. And 1,000 rectangles would lose even less area. And 1,000,000 rectangles would lose even less area. But if I want to lose no area, then I think the best number of rectangles to put in would be an infinite number of rectangles. That way we can perfectly assume the curve. Now if we put in an infinite number of rectangles, think about what's happening to the common width. Here we had a common width of 1/3. The more rectangles we put in, the common width will certainly decrease. And if we put in an infinite number of rectangles, then there will virtually be no width. Well, that doesn't make sense. We can't have a rectangle with no width, because then we wouldn't have a rectangle at all. All right, so consider the following. When finding the area under a curve using a right endpoint approximation, we already know, so let's start with some words. We already know that the area under the curve is the sum of the heights multiplied by the common width. In other words, this is your good old-fashioned base times height, or common width. Well, that's our base. That's the formula for the area of a rectangle. But in this case, we're going to take the common width and multiply by the sum of all the rectangles that we have. Now in mathematics we have easier ways to write this all up. We can, for the sum, we know the Greek letter sigma indicates that we're going to sum up something, and we're going to sum up the heights of all the rectangles. And we've seen over and over and over again, to find the common width, it's the difference between the endpoints divided by the number of subintervals. So that right there, b minus a over n, simply represents your common width. And for this particular example, we start with I equal to 1. Remember, this is your counter. So it says this is what we start with, our first rectangle, then we go to the second rectangle, the third rectangle, the fourth rectangle, and we stop with the sixth rectangle. So this tells us we're going to add up 6 things, and in this case we're going to add up the areas of 6 rectangles. Now, to get the heights, since this is a right endpoint approximation, we have to take the first right endpoint and we have to substitute it into the function. And we did that on the other side. Remember, we did f of 1/3 plus f of 2/3 plus f of 3/3 plus f of 4/3. Well, that's what this sigma does. See the little I right here? That's my counter. So if I expand this sum using my sigma, you'll recall that hopefully from pre-cal, that would be f of 1/3 times 1, which is 1/3, plus f of 1/3 times 2, which is 2/3, plus f of 3/3, which is 1, and that would be plus dot, 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 all the way to f of 1/3 times 6, which is f of 2, multiplied by the common width of 1/3. So this is just a short way to write what we already did on the previous page. So we said, how could we improve the approximation? We already talked about this. We're going to put in an infinite number of rectangles, because our goal is to lose none of that area and to calculate the exact area. So we have the definite integral as a limit. You'll recall that when we defined the derivative and we were using the slope formula, we wanted the delta x to be 0, but you can't divide by 0, so instead we approached 0. Well, same idea is going to come into play here. We already talked about how we can't let the common width really be 0, because if the common width is 0, then you don't really have a rectangle at all. So instead of letting the common width equal 0, we can let the common width approach 0. And the word approach hopefully brings back to your mind the idea of a limit. So let's see how that plays out. Take a look at the definition. It looks like what we had from above, but notice this time I'm starting with the first rectangle and I'm stopping with the infinite rectangle. So I clearly am putting in, I'm going to sum up an infinite number of rectangles. F is my function. Remember, to get your to get your endpoints, you have to take the first right endpoint, substitute it into the function, and multiply by the common width. So that's my common width, and this will give me the heights of my rectangles. I want you to keep in mind that all we're still doing is we're doing area of a rectangle is base times height. That's all we're doing. So area of a definite integral from a to b of a function, which is what we've been calculating, would be the limit as n approaches infinity. So we're putting in an infinite number of rectangles. We're going to start with the first rectangle and we're going to go to the nth rectangle. But we've already said that n is approaching infinity. All right, now this is my function f of. Now what the heck is all this stuff? Well, a is the lower bound. Now the question is, how do you get to the first right endpoint? So in the example that we had earlier, we were going from 0 to 2, and we had 6 partitions. So to get to the first right endpoint, what we literally did is we started at 0, and we moved one common width to the right, which was 1/3. So what we literally did is we started at the lower bound, and we added 1/3, which put me at the first right endpoint. And then to get to the next right endpoint, so now I'm at 1/3, so this is not a right endpoint, that's just where I started, so I shouldn't To get to the next right endpoint, I add another third, which puts me at 2/3. That's the second right endpoint. So 1/3 plus 1/3 puts me at the second right endpoint. So that's what this expression is all about. You start at the lower bound. In this case, the lower bound is 0, so it doesn't really have that big of an impact. The b minus a over n that we see right here, that's a common width. So we take the lower bound, we add a common width, and that gets me to the first right endpoint. Then we start at the last right endpoint, add another common width, and that gets me to the second right endpoint. So that's what the counter, that's what I is doing. It's moving me from the first right endpoint to the second right endpoint to the third right endpoint to the fourth right endpoint, and eventually to the infinite right endpoint. So this box right here, I know there's a lot of writing here, but there's a lot of stuff going on. That entire box represents the heights of my rectangles. Now the b minus a over n, it's steady. That's still the common width because we're still multiplying base times height. Okay? Now, that is the formula for, or that's the definition of area under a curve using limit. It will calculate and collect all of the net area bound by the curve. So I'm going to take the example that we did earlier, and I'm going to express that definite integral as the limit of a Riemann sum. In other words, I'm just going to expand this out so that it would represent the entire area that I want to collect. So I'm following the model that I have above, so I'm going to find the limit as n approaches infinity, which means I'm putting an infinite number of rectangles in so I don't lose any area. I'm going to sum up, so there's my sigma. I'm going to start at the first right endpoint, and I'm going to go to the nth right endpoint. And the nth right endpoint is infinity. All right, now it says to do f of. Now in this case, f is negative x squared plus 5. So in place of x, I'm supposed to substitute all of this stuff right here. So negative, take out the x. The lower bound, the a value, is 0. Now, hopefully you understand what I'm doing is just following. Let's change colors here. I'm just following this model right here, and I'm substituting the appropriate values. So a is 0 plus, now I take the common width, which is b minus a, so that would be 2 minus 0, which is 2. Divide it by n, which is the number of subintervals. And there's my counter I. Now the I is important because that takes me to the first right endpoint, the second right endpoint, the third right endpoint, etc. So that's negative. I put all of that stuff in place of x squared plus 5. So all of that right there, that represents the heights of all of the infinite rectangles. And then I'm going to multiply it by the common width, b minus a, so 2 over n. That's my common width. And that limit statement represents the exact area bound by the curve, negative x squared plus 5, the x-axis, and the endpoints 0 and 2. Not evaluating that yet. We're simply just expressing it as the limit of a Riemann sum. And these were right endpoints. All right, number 2. Now we're going to decompose a limit statement into a definite integral. So I'm still going to use the model that I have above. I'm going to erase some of that stuff. Let's make the eraser big so you can see the model a little bit better. All right, so bear in mind that I am going to decompose this statement. So when I look at example number 2, I'm finding the limit from the first rectangle to the nth rectangle. And all of this stuff in here, that was substituted in place of x in my function. So the first thing I have to find is my function. And one of the easiest ways to think about that is to take out all of the guts, if you will, take out the inside. So in other words, I'm going to take all this stuff out. I'm going to put an x back where it came from, and I'm going to put an x back where it came from. So I can see that the function here is going to be x cubed minus ln of x. That's my function. And I'm finding a definite integral in terms of x. The only thing I have left to do is to figure out the lower bound and the upper bound. Well, that's pretty easy because the lower bound is right here. Remember, that's where we move away from to get to the first right endpoint. So that's the value of a. So the lower bound is 3. And then over here, we have the common width, which is b minus a over n. So we know that b minus a is equal to 4. Here, let's write that here. b minus a is equal to 4. We already know that a is 3, so b minus 3 is equal to 4. So b has to equal to 7. So that limit expression represents the definite integral, or the area bounded by the curve x cubed minus ln of x, starting at 3 and stopping at 7. So that's how you find the exact area under a curve. It's the definition, or the limit definition of a definite integral. So now I hope you can use this to tackle your homework, which is in your packet or on Edline. You can take a look at that. It's on page 25. And all you're going to do is practice decomposing some definite integrals and then rewriting some expressions as definite integrals.